Welcome to Quantum Photonics. In a twist of scientific serendipity, researchers at MIT have stumbled upon a phenomenon that defies convention. Light, not heat, can induce water evaporation at unprecedented rate. Traditionally, we've associated evaporation with the transfer of thermal energy, but recent experiments have left scientists scratching their heads. Water nestled within a hydrogel was mysteriously evaporating at rates doubling, even tripling, the expected thermal limits. Enter the MIT team of Dr. Gang Chen, Professor Gang Chen, who, after an extensive series of experiments and simulations, have unveiled a revelation that could revolutionize our comprehension of this ubiquitous process. In a paper published in PNAS, the researchers disclosed their findings. Under specific conditions, light at the water air interface can trigger evaporation more efficiently than heat. This discovery challenges the traditional belief that water, a poor light absorber, relies solely on heat for evaporation. This phenomenon could have far reaching implications, from influencing climate models by explaining fog and cloud formation to transforming industrial processes. The team suggests it might even reshape our solar powered desalination, potentially eliminating the need to convert sunlight to heat first. What's truly astonishing is the researchers' identification of the photomolecular effect. By observing a hydrogel surface under simulated sunlight, they noted color dependent evaporation peaking at green light. This color specificity, unrelated to heat, strongly supports the notion that light is directly responsible for the accelerated evaporation. So, to tell us more details about the research is our very special and esteemed guest speaker, Professor Gang Chen, who is the Carl Richard Soderberg Professor of Power Engineering at MIT. He served as the department head of the Department of Mechanical Engineering at MIT from 2013 to 2018. He obtained his PhD degree from the Mechanical Engineering Department at UC Berkeley, and he was a faculty member of Duke University and UCLA before joining MIT in 2001. He received an NSF Young Investigator Award, an R&D 100 Award, an ASME Heat Transfer Memorial Award, an ASME Frank Krith Award in Energy, a Nukiyama Memorial Award by the Japan Heat Transfer Society, a World Technology Network Award in Energy, an Ehringen Medal from the Society of Engineering Science and the Keepers, and Marion McDonald's Award for Excellences in Mentoring and Advising from MIT. He is a fellow of the American Association for Advancement of Science, or the AAAS, the American Physical Society, the American Society of Mechanical Engineers, and the Guggenheim Foundation. He serves on the board of the Asian American Scholar Forum. He is an academician of Academy Sinica, a fellow of the American Academy of Arts and Sciences, member of the U.S. National Academy of Engineering, and a member of the U.S. National Academy of Sciences. Without further ado, I'd like to bring you, everyone, our very special guest speaker, Professor Gang Chen. Gang, welcome to Quantum Photonics.
Um, Thank you, Cecilia. Hello.
Yeah, I can hear you. I have a question for you before you start speaking.
Right.
How many, can your house still, can your medals and awards still fit inside your house?
I'm sorry.
Can your medals and awards still fit inside your house? Because I've just announced numerous awards and medals, and I thought sometimes, when someone would make a pass at me before, I will ask him, "Can you empty all your medals and compare it to mine?" And now I think I am being challenged, so that's my first
I,
question.
I can think of a few others.
Yes, so we are very honored that you are here with us, and we have pinned a link here of the link that you made, and we are very excited to listen to your presentation.
Thank you, and good evening or good day wherever you are. And really, it's my great pleasure and great honor to have the opportunity to speak to you today. And as Cecile generally introduced the work, it is indeed a serendipitous discovery. And in fact, we this is just at the beginning. We are in the process of understanding better. We are doing a lot more experiments, and we are trying to convince people, yes, this indeed happens. So I, when Cecilia invited me, I said, "Wow, quantum photonics. That's the right audience that people see might be really interested in this." So I gladly accepted the invitation. So if I could open my slides, I guess as I said, well, I should just click the link and then go to link, right? Because first time use it.
Yes, yeah, you can open it, or if you have a PC near you, you can also check your slides on the PC. And anyway, the audience will follow you through the slide numbers if you mention it from
Oh,
time
okay,
to time.
that's
Yeah,
good. Then I have it on
yeah,
my computer, so I don't open this link. I will just
yes, yes.
use my own computer. And uh, my talk today is really focusing on the paper itself. So this is a paper that was just published. And on the first slide, you'll also see a YouTube link. That was a talk I gave at Caltech. They put that on YouTube. This was a few months ago. And then I have also another paper on archive, which means it's not officially a journal publication. It's just a post, a paper we completed and we posted there. And this talk on the YouTube and the archive paper will provide, I would say, more even clearer, say, evidence. But today I will focus on this PNAS paper, which we have a title plausible photomolecular effect leading to water evaporation exceeding the thermal limit. And let me also introduce my co-authors on this paper. Yaodong Tu, the first author, worked with me for 5 years as a postdoc. And really painstakingly, she did the experiment and it's actually a lot of risk, in fact, for postdoc or work on things like this that you don't know at the end where it will land. Uh, and Dr. Jiawei Zhou was a former graduate student in my group, and he was working initially with Dr. Tu, and he's now postdoc at Stanford. And Dr. Shaotin Lin, he was a postdoc, joined to the supervisor with Professor Xianhuo Zhao, and he's now a faculty member at the Michigan Institute of Technology. And Dr. Muhammad Ashra, he was postdoc with me, and he joined me during COVID. Really, say we worked mostly remotely. And Professor Xianhua Zhao is a colleague in my department. He's an expert in hydrogel. So it's a really team effort, and I want to share with you how we got started. So the second slide just tell us the facts. The fact is, on the left, you can see is the solar spectrum, right? The green light, where we have most of solar energy concentrated at green, and they propagate. The green light propagate very long distance in water. So here we use an optical constant table of water and they show that it's 40 meters. So, of course, we all like to say clean water. We all like to say the bottom of clean water. And that is just a fact that because water does not absorb. And that's humanity. That's all we know. We know water does not absorb. So, the other fact is evaporation. And evaporation need energy, and pretty much all humanity knows is that we need to heat, thermal energy. And we know very well the latent heat of water and specific heat water, so you can easily calculate that if you want to evaporate a kilogram of water, how much energy you need. And of course, evaporation is a daily phenomenon. I gave three pictures. The first one is taken from web. I could have just slapped from my kitchen. And the other two pictures are the clouds, sunset, and this in some way all relate to the evaporation, right? If you look at the beautiful sunset, and after rain, when the cloud is when there are clouds, the sky is more beautiful. And in fact, I say we know that we always say that sky, this sunset is red. This is because the explanation of Lord Rayleigh just say the blue light is scattered. And after this talk, maybe we could even rethink this question: why the sky is so red in sunset after say when you have rain. And the slide 4 is so because water doesn't absorb, and we were interested in using sunlight to heat up water and recondense water, and this way we can do desalination. Salty water, we heat it up and evaporate and recondense to get fresh water. And so in 2014, we published a paper in Nature Communication. And the idea was very simple because water does not absorb. Why don't we put a black porous material on water surface? And that black material will absorb the sunlight, and the porous material will act as a channel to capillary force to suck up water. And that way we can create locally a hot surface on water and to efficiently evaporate the water rather than the sunlight go into the bottom of water. So in this case, our expectation is thermal. We want to improve the thermal evaporation, and we know the theoretical limit. You can easily calculate because we know how much solar energy comes in 1 hour, and we know how much latent heat and sensible heat of water to heat up 1 kilogram. So basically, using the basic energy balance and assuming all sunlight is converted heat used to evaporate water, and the maximum is about 1.5 kilogram per meter square per hour. And so we published a paper, and we basically forgot about it. We published a few other papers, but this was not really our main research. And this direction was picked up by a lot of people because of the application, the desalination, and so you can slide number 6 was a big surprise to us when 2014 Professor Guihua Yu from UT Austin, they did a similar experiment. But in our experiment, we used graphite, and he used hydrogel, and he incorporated black material. In that case, is a specific polymer called polypyrrole. It's a conducting polymer, so it's black. And the hydrogel they use is a polyvinyl alcohol. If you're not familiar with hydrogel, it's a basic jello. And so they use a jello type of material and put some black absorber. They did a lot of processing on material, and then they put it under the sun, and they got a evaporation rate on the right hand side. If you look at the right axis, don't look at the left axis. I don't think that's right. So they look at the evaporation rate. They got about 3, and the maximum is about 1.5. They got 3. And when I first saw this paper that published in 2018, I basically said, brush it aside. In fact, one of the co-author was my former graduate student. He was a faculty member, and but I didn't believe it. I brushed it aside. I said, this is impossible. This violated the first law of thermodynamics. And Professor Yu had an explanation. They say, oh, water inside the hydrogel is different. Their water that stick to the molecule, they call it bond water. And their water far away from molecule, they call that free water. And then they have intermediate water in between. And they say this intermediate water has a significantly reduced latency, and that's why they can get above the this say theoretical thermal evaporation limit. But anyway, I have to admit at the time I didn't believe in it. And slide number 6, I want to say on the left four of my heroes, Dr. Jiawei Zhou was a graduate student at the time, and he was working actually on semiconductor, but we started getting interested in the heat conduction in jello type material. He was working on hydrogel, started working on hydrogel. But we were working on heat conduction, we're not working on evaporation. Then I had a visiting postdoc from Shanghai Jiaotong University, Dr. Tu, and he came in and he wanted to work on evaporation under sun, solar evaporation, because we started that direction. And I said, well, I know Weihua's work. I don't believe it, but maybe we should test it. Why don't you go make this hydrogels? And at the time, I had a lot of visiting students. And this is Miss Hongxia Zhen, and she got her PhD now. So she was a chemist. And I said, okay, now we have a team. We can make the material. Hongxia was making hydropolymer hydrogel type of material. And so I said, why don't we try to repeat? And Dr. Shao Tunin joined us later. So basically, we spent a half year trying to follow the recipe Professor Wei Huayu had in the paper, but we couldn't make the material. So I called Professor Yu and I said, can I send my students to you and learn? And he was very generous. He said yes. And so 3 of them, Jiawei, Yaodong, and Heng Xiao, went to Professor Yu's group, and they spent a week there. And after they came back, they still couldn't make a material. You can see how frustrated I was. I said, what you guys did? But interestingly, they brought a piece back and measured indeed they had a higher evaporation rate than thermal limit. So we start to become real serious. So we say there's something here. And we eventually could make our own material, and then we got results similar to what they had. That's on the right-hand side. You see those black materials. In the middle is actually something I got in the lab, tried to make myself, learning to be a graduate student. It's not easy, but that was the a lesson I learned. So this is number 6. Let's go to number 7. And so I said, well, we are convinced, but what's the mechanism? I was not convinced on the mechanism, And I was suspecting whether there could be some photon effect because I work a lot of plasmons and thermal radiation. I said, is there a possible photon effect? So slide 7, rather than using a broadband solar simulator, which simulated the solar spectrum, we start to use the LEDs, different wavelengths. And on the left, you see the figure we measure when the LED was on the top curve. You see at different wavelengths, we measure different evaporation rate. And in fact, the peak happens at the green light. Green light, as I mentioned at the beginning, is the least absorbing. Water, say in green light can propagate 40 meters in water. So that was really exciting at the time. And if you look at the right-hand side, you will measure the absorptance of the material and as a function of wavelengths. And basically it's flat. It doesn't depend on wavelengths, but the evaporation rate depends strongly on wavelengths, a factor of 2 difference, right? And I would say, oh, we found the photon effect. I don't know what kind of photon effect, but I was very excited. This was actually end of 2019. It was a long time. And there's another puzzle. When we do this type of experiment, we also measure the air side temperature, the temperature above the water, the sample. And we did two ways, and one of this is using an infrared camera, put the glass will thermalize with the air and reflect the air temperature. And what was surprising is the right-hand figure, and you can see the blue dots when the lamp is off. This is slide A. And the red dots are when the lamp is on. And you can see when you turn on the lamp, you're adding energy into it, and it's actually cooler, right? The red, say, is lower temperature than the lamp off. And then there's this flat temperature region. And it was really puzzling. So we have these two puzzles in 2019, and but we could not come up. We said this is a photon. I said this is a photon effect. But we couldn't come up with a physical picture. What kind of photon effect, right? So slide line, you just say, what a possible photon effect? Could that be hot electron? Like I say, when light, this is a hot topic in photonics. So when light heat up a material, they can drive electron out of equilibrium with the surrounding and they become hotter than the surrounding. But this is unlikely because at that time there are a few papers from Professor Yu's group. They show different material all have this effect, including polypyrrole, carbon black, titanium monoxide. I said that's impossible to have all those kind of hot electron effects. And then we also had say, could this molecule say water molecule, or could this be polyvinyl alcohol, this PVA molecule? Is there anything special? But again, it's unlikely because it doesn't absorb. That's a fact we know too. So we basically in 2019 we were lost. We had this experiment. We just couldn't come up with a picture. And slide 10 is Professor Yu's picture, and he said, "Oh, water is different, right?" And in the polymer, there one's bound to the polymer, that's its blue region, and then there yellow region, that's what they call intermediate water, and then far away, the green region is bulk water. And this is a picture other people had before. He was using this but nobody really had proven that this kind of picture will lead to that reduced latent heat, significantly reduced. But then Professor Yu also had another paper. This is on the right hand side, and they put a hydrogel without the black absorber, but they put it on a black material, black carbon. A hydrogel will look like that. It's clean. It's clear. It doesn't absorb. And in this case, they still reported super thermal evaporation rate. And this, at the time, I thought must be a heat effect, thermal evaporation, because the hydrogel PVA does not absorb. So light goes through and get absorbed by carbon black, and that heat up, and then heat up polyvinyl alcohol hydrogel. So that's a thermal effect. We couldn't come up with our own explanation. We thought, well, we got to be serious of his explanation. So then slide 10 say we got serious. So we say, well, if it's thermal evaporation, why don't we do electrical heating? Why we don't use light anymore? So for 1.5 years, this is 2021 and 2020, half of 2021, we were trying to repeat with electrical heating. And because electrical, so we have to make our own heater because we need the pearls. We also needed to be close to the surface as possible. So on the bottom of slide 11, you see we have that position. That's where we put the heater. We were pushing closer to surface. So 4 millimeters, 3 millimeter to 1.5 millimeter. And we were improving the efficiency, but we could never go beyond the thermal limit. You can see the evaporation rate, right? It's 1.25. The limit is 1.5. So we couldn't get there. And of course, I had during COVID, and say I had the time to read, and to my surprise, there are many groups reporting super thermal evaporation. And on the bottom is all from Professor Yu's group. He used different materials, different absorbers. But on the top, you can see there people using different absorber, black material, titanium dioxide, polypyrrole, graphene oxide, carbon black, nanotubes. Then people use different polymers, biomass-derived melamine form, agarose, P9PAM, all different polymers, even cotton. And then some people took the polymer and they carbonized it. They carbonized fruit, they carbonized tree, and then become inorganic. And all those reported super thermal evaporation. And it was amazing. And so I had time to rethink this. I said, okay, we couldn't prove thermal. And we had 2019, this we saw the photon effect. Let's probably go back to photon and see what could be a photon mechanism. And it occurred to me that what are the common among all those materials? And the only thing common, this is slide 13, is they have a lot of surface area. All the samples have a lot of surface area. And this is the one I started to ask, can this be a surface effect? And I ask, what kind of surface effect? Immediately so it becomes clear to me there's a surface effect, that's the photoelectric effect. Photoelectric has both bulk and the surface, but surface, because the electron has to come out. So of course we know the photoelectric effect was what Einstein really started the modern physics, and turns out the experiment was done by Heinrich Hertz. And Einstein explained it using the photon idea. So then I ask the question whether photon can lock out water molecules directly. And this is not one photon to one molecule, it's actually one photon to lock out the many molecules. So slide 14, of course, there are problems. One is water doesn't absorb, right? So green photon doesn't even interact with water. That's a puzzle. And second, and this is slide 14, and the photon energy, the green zero point 0.5 micron is 2.5 electron volt. And water are bonded by hydrogen bond. Those are the water between water molecules. The bonding energy, hydrogen bond, is about 0.26 electron volt. So there is a big energy mismatch. But then, say, I also read a lot of paper, and in fact, I wrote a review on liquid, and I learned water molecules are really water is the most complex liquid. That's people work on water says. And this is because they form cluster and hydrogen bond network inside the water. And people all agree on this, but it's so complex, people don't agree how big are this, the network. Some people say just say 4 molecules. Some people say 300, 400 molecules. You can see the range. And but while the idea is if they bond it as a cluster and if they come out as a cluster, then they have a lot of bond, and that bond energy together can match closely to the photon energy. So the energy matching is not the real problem. And then this is slide 15, just to show the different water cluster picture, and that there are really wide range of work on this. And slide 16 is a physical picture, because we still need a driving force. And this is what convinced me more. I said, here is a basic Maxwell equation. So Maxwell equation says at an interface, here we draw, let's say on one side there's a vacuum or air, the other is water. When light comes to interface, at the angle, there is an electrical field component perpendicular to the surface. So we use a perpendicular sign. And epsilon 1 and epsilon 2, this is slide 16. Epsilon 1 and epsilon 2 are dielectric constant. And air dielectric constant is 1, and the water is 1.8. So the Maxwell equation boundary conditions say the displacement field, which is the electric field, dielectric constant times electric field. And the boundary conditions say in the perpendicular direction, this displacement field must be continuous. And that's a requirement of boundary condition, Maxwell. We didn't invent this. And so now if you look at the interface, and people have done molecular dynamic simulation of water-air interface. And that interface, the simulation just say is a few molecule, just a 5 angstrom thick. So what this means is over 5 angstrom distance, the perpendicular electric field changed by a factor of 2. And this also means that over a water molecule, which is about half angstrom, the electric field acting on oxygen atom and hydrogen atom, they are different. So the force is the charge times the electric field. So the force will not balance. So basically, what we're saying is water molecule is a dipole at the surface. Under electric field discontinuity at the interface, the water molecule actually experiences a net force. And this, we call that quadrupole, because the dipole, you expand it and it's quadrupole. So basically, this gives a driving force. We still do not have a quantitative model, but this is a qualitative hand-waving picture. So with that, I said, well, maybe hydrogel absorbs. We didn't know. So I told Dr. Yao Dong Tu, this is slide 17, I said, why don't we test this hypothesis? Why don't you go dry the hydrogel and put a little water? Do not put much water because we need a water-air interface. So slide 17 has three figures. On the left, on the bottom, so we measure reflection, we measure transmission, so we can get absorption, because absorption is 1 minus reflection minus transmission. But hydrogel is scattering, so we have to be careful. On the bottom, the top two figure, we show how we do measurement. We use this so-called integral sphere. So the experiment has uncertainty, and on the left bottom figure, figure, at the bottom you'll see water, you'll see as-gelated PVA hydrogel, and you'll see PVA powder. Basically, between 500 to 700, you can see they are close to 2.5, but basically close to zero because the rest is experimental uncertainty. And then in the middle figure, we made the gel, we dried, right, freeze dried. That's the bottom figure. So that's a dry hydrogel. And then we add a little water, and you can see the absorptance increased significantly, and get to 20%. And what's amazing is this material doesn't absorb. The hydrogel polymer doesn't absorb. The water does not absorb. But when you put them together and they absorb, there's no black absorber here, right? And that is an experiment. This is our turning point. This was actually in the middle of 2021. And after this, everything become fall together. So the slide 18, we go to measure evaporation rate. And in this case, on the left, we have a pure PVA curve. You can see the sketch shows there are two stages. On the first stage, when water really cover the entire surface, we don't see high evaporation rate. And then when on the second stage, we see the high evaporation rate. And we could also, by that time, make the same sample as Professor Yu makes. That's a carbon paper, put a clear hydrogel on top. And this is a middle figure. You can see when we shine light from bottom, the evaporation rate is normal, doesn't have a high evaporation rate. But when we shine light from top, goes through hydrogel, we see a stage 2. So that's much higher. So on the right, you see we could go, all the sample go into super thermal, above the thermal evaporation limit. Slide 19 shows that the left figure shows the wavelength dependence. This is a null absorber, null black absorber. It peaks at the green again. And we still don't know where it peaks at green. It's just amazing. It peaks at the region water is the least absorbing. And this is something that still puzzles us. And slide 20, we measure, again, pure PVA null absorber. We measure the temperature of the vapor above the surface, the air, and we again see that flat region. And if you just heat up water by electrically, no light, you don't see that. So why is this? Now it become quite easy under a picture. This is the right-hand side figure. When light cleave off this water molecular cluster, they dissociate in air because they collide with the air molecule. And once they dissociate, they will saturate the air. Once they saturate the air, the temperature becomes flat. So that's So that for us, it become a very straightforward explanation under our picture. Slide 21 shows the spectrum. This is where a lot of reviewers they don't believe it because they say you can't possibly measure. We don't know exactly what are the cluster we're measuring, but we measure the signal above water surface under light and compare without light. We see the blue and red shift of the spectrum. And the way interpret this as the result of cluster cleaved off by the light. So that's basically what this paper is about. And let me just say, we by slide 22 explains why it was hard to make this sample. Because what we know is that there's a porous material and light cleave off the cluster, but they can recondense inside the material. If they recondense, because we're measuring the weight loss, we will not be able to measure that as a weight loss. So it become a heat generation because during condensation, they release the latent heat. So you have to really make a material work, and that's why we spend a lot of time. We still don't have an exactly good guideline how we can make the material. So we call this their internal effect and external effect. And finally, slide 23, just to ask, we think this is have this effect really raise a lot of interesting questions, right? Is this why they happen? Because of the interface. In hydrogel, actually doesn't matter as long as they're water air interface. So in clouds, in fog, in ocean surface, soil surface, plants, right? And how does this affect the weather and global warming model? Because the clouds absorb and evaporate. In fact, we found now that there are 80-year mystery. Experimentally, people measure more absorption than what the past theory could calculate. Now we think we provide an explanation. And the global warming, because the water is actually twice more greenhouse potent than, say, CO2, because there's so much water in air. We don't call it a greenhouse agent because water condense, but it's a positive feedback mechanism. Why the effect peak at the green? We have no idea. Does it happen in other liquids or even on solid surface? We think so, but we need more experiment. How we do we quantitatively characterize the effect? How we model it? And the last one is the question we asked immediately after I realized this, but I actually got a lot of questions, similar questions. Why does this effect explain why plants reflect green light? Is plants reflecting green light evolutionary? This is not because of the photosynthesis. So why they evolutionarily avoid the peak of sunlight, right? So with that, let me open for question. I want to thank many people. Those are they left my current group members, and on there are many professors, not all of them are in this there, and I want to thank you. And so let me stop here, and hopefully we'll have some good discussion.
Thank you so much, Professor Chen. And I really, really appreciate the slides and the last portion of your slide here, asking significant questions, because I believe even if we make a benchmark discovery, I believe that the end result also of any experiment is to discover something and then ask further questions. And I really love the questions that are being asked by your team. So we really look forward to the continuation of these works. And in fact, while I was listening to you, I was asking this question like, why does the photomolecular effect peak at green light? And I noticed that there's a lot of research about light because basically, of course, I think Eric, who is our co-moderator here and is a regular moderator in quantum photonics, has done some, color therapy sessions. And at the same time, I think in quantum mechanics, while they're trying to study quantum dots and also entanglement, they tried to make some gradations of light on why there is an effect on the molecules of different lights when they try to guide the quantum entanglement. And so they have observed different reactions using different lights like orange and yellow and blue, for instance. So yeah, I'm very curious, because the significance of your study could lead to other discoveries in other disciplines. So anyway, thank you so much for joining us. And we are here to reset the room. I would just like to say that we are here to listen and also discuss and ask questions to our eminent guest speaker, Professor Chen. And please check out the link that I had posted about his lecture in YouTube. It's in YouTube. I think he lectured in Caltech, and it's about rethinking evaporation. And just to reset the room, I would like to introduce our guest speaker again to those who just came in. And after that, I will pass the mic to the speakers here on stage and the other members of the audience who would like to come up to ask questions. Just please raise your hand and we will bring you up. So, Professor Gang Chen is the Carl Richard Sordenberg Professor of Power Engineering at MIT, and he served as the department head of the Department of Mechanical Engineering at MIT from 2013 to 2018. He obtained his PhD from the Mechanical Engineering Department at UC Berkeley, and he was a faculty member at Duke University and UCLA, and before joining MIT in 2001. He received an NSF Young Investigator Award, an R&D 100 Award, an ASME Heat Transfer Memorial Award, an ASME Frank Keith Award in Energy, a Nukiyama Memorial Award by the Japan Heat Transfer Society, a World Technology Network Award in Energy, an Erin Medal from the Society of Engineering and Science, and the Capers and Marion MacDonald Award for Excellence in Mentoring and Advising from MIT. He is a fellow of the AAAS and the American Physical Society, the American Society of Mechanical Engineers, and the Guggenheim Foundation. He serves on the board of the Asian American Scholar Forum, and he is an academician of the Academy Sinica, a fellow of the American Academy of Arts and Sciences, member of the U.S. National Academy of Engineering, and a member of the U.S. National Academy of Science. So that's our guest speaker for you guys who are listening to us. So please come up later and ask your questions. In the meantime, we have our very able co-moderators here, Eric and Rishi, and of course Bob, who is my mainstay moderator. Bob might have a question later, and also I think he will be reading some of the questions and comments here at the room chat. So, whoever wants to speak first among the speakers here, I'd like to pass the mic to you. Just flash your mic. Yes, so Rishi, yeah, I'd like to pass the mic to you.
Thank you. So in India, we have a practice where we use an earthen pot, which is a porous material, sometimes clay, but largely very porous earthen pot, and we fill this with water, and the water from this pot is allowed to evaporate gradually, and it keeps the rest of the water inside the pot cool, so it gets us like cold drinking water without having to refrigerate. So the mechanism of the pot allows you to retain most of the water. So like 80%, 90% of the water stays back in the pot, and just what you need to cool it down with evaporation is allowed to evaporate. So I'm just picturing that in this mechanism the air water boundary is maximized in terms of surface area, and that would sort of like since it keeps replenishing itself, the earth is absorbent, it would keep uh, pulling in more water into the air water boundary, and you would have like this constant evaporating surface. um so I guess my question would be, are there any materials that any membranes that let us simulate something like that where we keep getting water maximized to the surface?
Excellent comment, and I think they're really. I think this is a first. What you describe is thermal evaporative cooling, and when you evaporate, you need say absorb energy, and because you need to supply the energy needed to overcome the latent heat. So. The evaporate cooling is in fact a widely used technology. People, particularly in developing region or underdeveloped region, and when people don't have enough electricity, you just use evaporation to cool the area. So there are a lot of different approaches, and what they describe is using porous material to sort of control the evaporation rate, and then we do actually work on that too. So um, the specific process that we describe here is you need a light to actually photon to cleave off water molecular cluster. That's the what we call photomolecular process, and this process does not need the thermal energy. It just like life, just like say a ball you threw water, just say lock out the water droplets. In this case, it's not a water droplets, a photon ball coming in and lock out a cluster of water. This cluster we currently actually estimate probably contains around 20 water molecules.
Yeah, I'm quite sure that the evaporative cooling that we expect from this pot might be largely due to thermal cooling. But in my experience, it's we want cool drinking water, so we don't like to keep it in direct sunlight. However, keeping it in direct sunlight does increase the rate of it, not the rate of cooling, but the visible condensation around the pot. Although that also evaporates quickly. But I guess I'm asking. Um, uh, we expect some amount of. I believe it's not just thermal, but just the fact that there is a water air barrier. It does allow for some passive evaporation. If you could correct me if I'm wrong, but even at room temperature or a slightly colder temperature, just the fact that the water is exposed to the air does allow for some evaporation to happen at the boundary. I guess my question is, if I had a pot in the sun, and that porous material did allow for the water molecules to be at the surface, what percentage of the evaporation could be attributed to this non-thermal process of just exposure to air causing some water to evaporate, versus I think that happens also on ice, like on glaciers you can see a mist rising above the glacier because even though it's very cold and there's not much latent heat to be absorbed, there's still some amount of evaporation of water vapor from the ice. So similarly, like what percentage of it might be attributed to thermal and what percentage might even be from this photonic reaction?
That's a really good question. I don't think we have a good answer at this stage. That's why I say characterizing is separating those effects. What I can tell you is that based on this, you can actually read our archive paper, and then based on our work on single water air interface, we think when green light come to surface at 45 degree, the a single interface could have about a 0.8% absorption, and well, compare how much is thermal. We don't know yet. We don't know uh, the when we let me say this, when we put the a single interface, when we heat up water to about 30 degrees, we have thermal evaporation. We measure rate, and of course that also depends on the wind speed. And then we put on the light, and we have an additional few percent in say is that few percent, probably around 10% increase at a single interface at that temperature. So the thermal evaporation depends on temperature. The light evaporation, we haven't done systematic of how dependent it is on the temperature.
Got it. And
Uh,
sorry. Um,
just say
yeah. So
this is
um,
all wide open. That's
and I'd like to also ask if light was incident on the water molecules. How much would you attribute to some photovoltaic absorption of the light, and how much would you attribute to some thermal excitation because the photons sort of being absorbed into the water?
well,
That
night,
are both of these like accounted for?
green light doesn't absorb. It just say water does not absorb pretty much green light. So you should not say if you have say no other black material in there, you don't see any heat up, and but say it actually evaporates. So that's the amazing point there.
So you would have both, but when you use black material, you do have both, and when you use green material,
Yeah, we
you
have
don't have both.
determined now that we don't have an answer. We do not have an answer. That's a good question. That's what we're hoping more people work on it.
Okay, thank you so much. I might come back with another question later.
Thank you, Rishi. So yeah, I don't know if Ayo or Eric
Yeah, I'm
wants
here
to
now.
speak.
Sorry, my apologies. Yeah, so interesting talk. We also had a similar effect in the radio frequency range. Our team noticed similar effects. I think this exists across spectra, across many electromagnetic phenomena, specifically with water. Um, I personally really liked the description of the methodology that you had. If you could speak a little bit more to that about the deductive process, because it seemed like you had to touch upon all these aspects, and in the end, it sounds like boundary layer separation due to photo interface phenomena is how I like summarized in my mind. Well, what seems to be happening, and of course the nuances in the incidence and transmission, reflection, absorption. But if you could comment on that, that'd be great. Thanks.
It's the deduction process. It was I was uh, part of the reason I was telling all the history is indeed was you can see the science is you get the puzzle is at the beginning of just say it's impossible. Uh,
For some of the experiments we did, we had to basically convince labs, and 3 labs said no for some of the experiments. So it was surprising to us the unwillingness of people to try new things. And when you discover a new phenomenon, like for us, it was hey, viruses can be detected up to a gene difference using only radio waves in the microwave range, something like up to 6 gigahertz, which was kind of ridiculous. But then we just went ahead and did all the measurements, and we went through, okay, what's the biggest one? What's the smallest one? Is it in this kind of water, in that kind of solution? Does the surface make a difference? Is it hydrophobic or hydrophilic? Does that make a difference for the interface as well? So I found that to be a very fascinating process. As you were describing it. In terms of technologies, you mentioned also the green light. So I'm thinking immediately, okay, let's start stimulating organic samples with green light and see what kind of effects we can get. Usually, it's not the kind of light that's used for stimulating samples. So that's also a very interesting avenue. If you had any comments on that, I'd love to hear them.
yeah, so this was also related to asking this why leaves shine away from the green, right? And we see green because they reflect green. They say they don't like green light. And then you look at the coral reef, right? They also have photosynthesis, and they are underwater, and they are not green. So the evolutionary when these plants go from say the ocean to land, uh, did they develop say because this effect is too strong, they lose too much water. I also got other questions. The let's see from an email, and people ask, "Oh, is this green driving the say evaporate the evaporative process because plants they need this transpiration to supply water to the leaves." So all these questions. Um, at this stage, in fact, I also have to say, even though we ask this question, I need to say who is willing to work on this, right? Because that's just a sort of blue sky type of question, and
Blue sky, green field, though, because I think green field because it might be easy to replicate some parts of what you're doing. So I'm thinking, what kind of experiment could we do in our lab that complements yours? What kind of equipment did you use? So, like, that would be some of my questions. If you're willing to discuss some of those technicalities, that's something that we would be willing to take up because right now we're marrying RF and photo effects for the purpose of rapid pathogen identification. If we could leverage some of the results that your team has discovered and make some headway with either creating a model or advancing this work, that would be very fascinating. So, like for us, we use a vector network analyzer, which allows us to measure the impedance of the resonance of the sample to the antenna. So that's kind of one of the pieces of kit, and those pieces of kit range from about $1,000 to $1 million. So depending on how precise you want your science to be, but we're also trying to commercialize some of these aspects as well. So
well, that's wonderful. Yeah. So the equipment that so far we use are not expensive. Let's say for those experiments, it's basically balance and the LEDs, and those are all very cheap. But see, when we do a spectrometer, right? Let's say then that's say like a piece of equipment that more expensive. We'll say 50K to 100K range. And at the article we put on archive, we use the laser because there we could control polarization because we would really show the light that need to come at the angle, need to again there we
we
also.
did polarization with a lens. We used a complementary split ring resonator as a lens, and we polarized the light using the metamaterial surface itself. So I'm wondering, hey, what kind of interface would you have if you married two phenomena like RF and photonic? Because we also have similar curves to what you have. There's like weird spikes in certain ranges and weird dips in other ranges, and quite as you so pointedly put it, nobody really knows why. It's just, hey,
So
here's the curves,
send
and
me,
that's exciting. So, yay, we could do something with that. But other than
send
that,
me an email. Maybe we can chat more on that.
yeah, would love to. We'll connect.
Yeah, yeah. This is why I want to talk to people. Yes.
Yeah, thank you, Eric. And we welcome Vincent who came up on stage. And to the audience, just raise your hand. If you have questions, we will bring you here on stage. And before going to Vincent, there are questions here that had been sent to me. So this is by Araceli Jones. So she said that you mentioned that the photomolecular effect might be happening widely in nature. How could this phenomenon impact climate, and are there specific natural processes that you believe might be influenced by light induced evaporation? That's her question. Would you like me to read it again?
Yeah, that's fine. And this is a let me share a story on this. When I first thought about this, and so I tried to convince my wife. She's accountant, and she first didn't believe me, and after many times, she says, "Oh." The weatherman, when she started believing me, she said, "Oh, the weatherman say after sun burn the clouds," and so that actually promoted us to do experiment on clouds, and then we found that the green light can heat up clouds. And then it was actually this year. I looked at say I had a student, visiting student from ETH, and I asked her to simulate this effect using Monte Carlo and first on hydrogel. Then I said, why don't you try clouds? And she did the simulation, but what's surprising, she came back and she said, hey, I found there's an 80-year mystery in the atmospheric science. And the experiments done by that community show clouds absorb more sunlight than the current theory can calculate. And the current theory is just to solve Maxwell equation based on the water property. And because this measurement is so hard, people fly airplane on top of clouds, say below the clouds, or they use satellite data, and the clouds is not something easily controllable. So there are arguments. Theoreticians say this is impossible. The experiment is wrong, and that's been there for 80 years. And now we think we have an explanation, and it's just a hand-waving one, right? Because we don't have a real quantitative theory for the effect. But and why this is important? Because this is also that community say why they those experiments, the controversy is an important result because the entire atmospheric water cycle is driven by this, right? Because you think about the say orbital region, the say the equator region, and you think about pole region. Pole region is cooler, and the equator region, the pole is hotter, and the entire Earth water cycle is depends on this. So but how this would affect the model? We are at the stage we're trying to tell people this exists. Please pay attention. Maybe, yeah. So we don't know how eventually we're going to integrate or how this would get it. But we think it's going to be important.
Yeah, thank you. So, yeah, we'd like to give the mic to Vincent, who just came in on stage. And after that, there's another question sent to me. Vincent, welcome to the stage.
Great to be back. Bob Cecile. I Des- Desel. I just have to say, this is incredible. Um, just if you could give me a minute to compile my thoughts, so many questions.
If I could take a minute, I'd like to just maybe ask out loud. There are I think the basic uh, organic molecule that's capable of photosynthesis is called a chromophore, if
Hiroshi, is
I'm
it
not
possible
wrong.
for you to fix your mic? It's really low. I'm sorry to interrupt.
No?
Yes, much better. Thank you.
Okay, thanks. I believe the basic organic molecule capable of photosynthesis is called a chromophore. I might be wrong about that suffix there, but it's what algae that are capable of photosynthesis, and it's also like an ancient microbe which was used by plants within larger chlorophyllic structures. So it's sort of like, it's become a part of the plant genome, and it's almost a symbiotic relationship. So I think it's checking how these chromophores how well adapted they are to photovoltaic sort of using photovoltaic energies or channelizing the photovoltaic aspects of sunlight rather than the thermal aspects. I think we're looking at like the looking at how these the physical structures are designed, if they're more tuned to voltages rather than thermal excitation, then we might look more towards uh, um, electrovoltaic effects causing the water light interaction that we're talking about here. But if these molecules are more attuned to like thermal excitation, maybe it's we can expect more relevance for heat energy transfer from the light.
Yeah, the chromophore, of course, that's why how the plants do photosynthesis, and plants photosynthesis use the red and purple range of photons, and they that itself you can understand that as a photovoltaic effect. Basically, the photon get absorbed and generate electrons, say lift the electron from the lower energy level of the molecule to higher energy level. What we are talking here, we call it the photomolecular effect. And it just doesn't, it's not same mechanism like photovoltaic. We think it's a purely surface effect. It doesn't happen in bulk water. That's say the granite, they can propagate 40 meter, as I said. It doesn't absorb the granite, but somehow it just get absorbed. The process happen at the surface. We presented a hand woven picture. It's not a rigorous model, but that picture just to say sort of convince this process could happen, and then we went to test. So that's basically where we are at this stage.
Yeah, so there's another question. Rishi, do you have a follow up question?
No, thank you.
Yeah, thank you. So maybe in a while I will pass the moderation to Bob because I'm losing my voice. But there is a question which was sent to me here. This is by Eric Clarkson. You mentioned that the photomolecular effect might be happening widely in nature. How could this phenomenon impact climate, and are there specific natural processes that might be induced by light induced evaporation? And also, the second question is, beyond desalination, are there specific clean water technologies or purification processes that could benefit from harnessing the photomolecular effect? How might this discovery be applied to address global water scarcity issues? Maybe focus on the second question because the first question was by Araceli earlier. I mistakenly read it. So the second question is, beyond desalination, are there specific clean water technologies or purification processes that could benefit from harnessing the photomolecular effect? And how might this discovery be applied to address global water scarcity issues?
Yeah, that's an excellent question, and I think it's our hope that this effect will be explored by many people for different applications beyond the desalination, which is where we started, and of course, desalination with water treatment. Another big direction we think could have this effect could be explored is in the drying process. In terms of the drying use about 20% of all the industrial energy usage. So if we can accelerate the drying, we can make the drying more efficient. Basically, using the same amount of energy, we can dry more water, drive out more water. Will be more efficient and make the process faster. So I think there are those say those are the say direction we are actually also interested in exploring ourselves. But to us, this is wide open. Really, uh, if there, uh, if it's a process that that's new, people haven't thought before, we hope that this could stimulate more thinking and more applications.
The only thing that I'm concerned about is the, as you jokingly said, you're like, what were you doing there for the 10 days or a week that you were there? And you couldn't synthesize the chemical. or the chemistry. So the chemistry, I think, is the interesting thing. If the chemistry can be scaled down to like industrial levels, like quite literally, it has to be dirt cheap, made out of dirt, preferably if possible.
Yeah,
So, what do you have any estimates or costs on the manufacturing, or
I
what the difficulty laying ahead might be?
yeah, I think that's where for different application because like I said, the clouds has the same effect. You don't need any material to make clouds, right? But of course, for different applications, say as I explained in one slide, you have internal, you can cleave off this molecule and they may recondense, then they don't get out, right? So then this might be a limitation of what you're drawing, and then maybe then can you design the engineering process that you can favor this process to happen, and then we just need more study there. I don't have any silver bullets at this stage.
Well, that's where the next meeting will come and be exciting because I think uh, as I listened to the lecture, I realized the nuance, and there was so much of it. It's like Lisa needs braces, dental plan. Lisa needs braces, dental plan. Eventually, you put the two together that they're connected. So I'm still trying to digest the various avenues here, and as you said, the accelerating the process. Would be the kind of the engineering staple. I know there is, as a reference, I know there's an Israeli company that does solar evaporation using very shallow hexagon pools, like a mesh of hexagon pools, and the water circulates in the hexagons, but they're not very tall. So I wonder, and they're able to do water heating and all these other things. Some of the desalination um, technologies probably leverage that as well. So I'm wondering if it's not already used unintentionally or unknowingly by some of these engineering designs. I'll try to pull up the exact name of the company here. I just need a moment to find it.
Yeah, that's this is a process that we think exists in nature. When you see sunset, I mentioned at the beginning, right? Of course, say we know that the basic effect people think is really scattered. Blue lights are scattered. That's why what's left is red. But then you ask why they change so much under different clouds. Why they wouldn't have clouds? They have even redder. Maybe it's related to what we see here. Maybe blue light is absorbed more. We don't know, right? So the when you talk about this example, I ran into a hair dryer. Somebody was say design a hair dryer and they have a blue light. They were the green light. They were so excited. So I went to actually say this was a company in Shenzhen. I went there and talked to them, and turns out that they avoid it. They use the green light just for beauty, and they actually filter the most green light out. But even that, they still have a pretty neat hair dryer. So yeah, sometimes the process might be there. People are using it, and they just don't know it.
Yeah, yeah. So the last company that I'm familiar with is called Fovia, Phovia, and they're a veterinary epidermis healing accelerating some sort of stimulator. It looks like a fancy flashlight, but it has a lot of green in it. And so they have some fancy sequence that they run on their lights, certain frequencies and order. And when my dog recently had surgery, they used this on his paw to help him heal because it was like snowy at the time. So the snow made the infection much more of a risk factor. So for to reduce the overall time sensitivity of the risk, this treatment was suggested, and over the course of 2 or 3 treatments, within a week span, all of the skin was almost completely healed and much more healed, much more quickly healed than other technologies. And we only heard of it because our vet is from South Korea, and he always uses all these cool and fancy new technologies. So that was the last, I think, industrial example that I'm familiar with that uses some sort of weird green light phenomena. So But I'll definitely be bringing it up in our meeting, and I also sent you an email, so hopefully it gets through your spam filters and so on.
Sure. Yeah. Wonderful.
I had a question on the drying. Would you be able to say that if we were drying some plant material, say some fruit or vegetables, it would be better if the vegetable was not green and therefore it would dry out more easily? Because if it was green, it would absorb light away, sorry, reflect right away.
Well, so the of course the green plant itself is green because it's reflecting the green light. The um, um, uh, but when you dry, you will lose the green, right? It turns out the green is the most effective in this process. So how to optimize the process? We don't know. Maybe at the beginning you don't use the green light, but later on you switch on the green light. So so those are the things that assuming what I say here is all right, then it's a fundamental discovery that the people really can think how to best use it.
Thank you.
Yeah, thank you, Rishi. So I would just like to comment on top of the comment of Eric a while ago. As you see that there are industrial uses, for example, with your dog who had surgery, using light, I could say that this is a big industry, especially in Asia, because in terms of aesthetics, because they use different kinds of light to rejuvenate and also try to for dermatology. So there are different lights that are being used, and it's a big business. Actually, I did not see any study about that, but it's so expensive, and now I think it's becoming more ubiquitous. So yeah, it has some good effect, but I haven't seen as a formal study on this. But I would just like to mention that. So anyway, I have a follow-up question for Dr. Chen. You are trying to rethink evaporation. And in any kind of education, especially if we will be looking at future researchers who are now taking their core competency education, of course, they will be taught by their schools, primary and secondary schools, about the process of evaporation. And of course, they will be taught based upon the traditional way in so many years, actually, that we had been taught about that particular process. So, how do you think is it possible? Of course, this is not your job, but I was just thinking because I worry about problems that are not mine most of the time. But I was just thinking, how will we be able to do an educational outreach for professors, for instance, because this is what they know, the traditional way. And now that we are rethinking evaporation, because you have made a benchmarking discovery, how will we be able to do educational outreach and instruct the professors to keep an open information from your side of this study? So, are there any outreaches that you are doing to here?
Cecilia, you're really thinking say ahead. Thank you for thinking about that. Our current thought is, in fact, uh, this is so unconventional, and our first job here is trying to get more people repeat and demonstrate. It's not just from us, but it's verified. Say this experiments are true, and then hopefully getting more people understand it. But I think once it verifies true, yeah, we should see. I do think this is the type of knowledge that should get into the say middle school, high school, or even because the evaporation is ubiquitous, right? So, but I think the first step now, say in front of, at least for us, is trying to convince the scientific community. and having more people to check. And we might be made some stupid mistake. We don't know. We tried. This is like I said. We started 2019, and we just started publishing. And hopefully this will draw more attention and more people test. And I'm fully expecting that this is say there will be debate. There will be say hopefully eventually we will say we could be proven by others. So yes, this is indeed a process that happening, and then we need to do education. I completely agree with you.
Yeah, because I think that this is a very important basic foundation of their education, and also to question. Because, for instance, with this age of technology and artificial intelligence, we could see that what we had known 100 years ago and what has been our benchmarking model 100 years ago and has never changed changes overnight, and it is in fact exponentially changing. For example, I studied neuroscience several years ago. I mean, many years ago, and then I revisited it on 8 years ago. And yeah, I went to the real details, and you see that even our professor Idan Sigeb of Israel had also rediscovered something that should change in what has been fundamentally taught, in neuroscience. And yeah, this year's because we have the coming of technologies like even in microscopy, metamaterials, and many others that has changed the way we are able to do our experiments. And of course, artificial intelligence has been here. So many things have changed, and a lot of dogmas in the past had been overturned. So I think it's, if we could not catch up with this kind of new information, and I know that you wanted your experiments to be validated and to persuade other people on your field to duplicate your experiment.
We'll
So
be trying
I
to duplicate them. We'll be trying to duplicate them. So there's one for you.
Great, great.
yay. Yeah,
Yeah.
so yeah, I think the world should be trying to rethink, the model that they have for education. Because because if we try to teach something which has changed already, we are going back, to we are going backwards, and it's not really good as we are really advancing with all the information that we have. So in fact, of course, it's uh, it's not only the technology, but the ubiquity of connectivity, communication, and information, which you could get at the tip of your mouse or on your phone. In the past, right? If you were trying to make some research, you have to go to another country or wait for the documents to come. But now, if you wanted to discuss with fellow scientists, or if there are people who had made a similar experiment as you have, it's quite easier. So I would just like to wish you kudos, and I hope, is there a next step for this experiment already coming in? I mean, for a next study among in your lab?
Yeah, we pretty much all focus on this. As I put on that archive, you want to look at that, and there we're working on a single water-air interface. We had we counted 14 different experiments to test this, and at least so far everything checked out. So we believe it. And again, in fact, we in the process we had made mistakes before, say in the process, and we had to spend another year to check. And we that's it's a long process, but yeah, this is something that worth checking and see and get other people validate.
Yeah, it's interesting because the way that we phrase it, because saying that you're going to reaffirm your hypothesis, like technically that's that's not science. So I've gotten flack for that in the past. So now we just say we failed so far. The great news is we failed to disprove the model. Isn't that great, everyone? Fantastic! We failed. It's
Yeah.
wonderful. All these experiments, and we failed to disprove the hypothesis. Great work, everyone. So
Well,
that's how I phrase it.
well, we can always thank Karl Popper for the falsification process on that one.
Yes, so there's another question here from uh, Bob, Bob Chu. So it's about the nanotechnology integration. Maybe he saw some of your slides. So, considering the unexpected absorbing properties of partially wetted hydrogels, do you foresee potential applications in nanotechnology, perhaps in the development of advanced materials with light absorbing capabilities?
That's a very good question. Yes, I do. What excites us is if you think about what basically what we know the way to have absorption. One is due to electron excitation, so the electronic absorption, and the other is due to the atom vibrating. And here we think basically there's the third process, which is it's related to also laser ablation, right? Basically, it's a process. Think like you got a photon coming, you lock out the material. And of course, in our case, if you do design, they can recondense, I mean, become just a generating heat. But see, it's a completely different way of absorbing. So we do think there could be potential new applications.
Like I immediately think of, hey, you want some more energy to break apart these molecules? Here, go through this special tunnel this way. And then you can engineer the parameters or specifications of the tunnel according to some of the phenomena here. So, like, I'm already thinking microfluidics. So a bunch of things come to mind, at least from a nanotech perspective. But I will say, I think the universities always want you to hold those cards close to your chest for IP reasons. But then you have to share because progress happens when you share ideas. So it's an interesting balance. If you're willing, would you comment on that? Because I think that was something that was surprising to our team, the amount of eagerness for everybody to patent things, and we're just trying to discover a phenomenon. And if we shield everything with intellectual property protections, nobody's going to want to touch this stuff. So
Yeah, well, that's you can say we put our paper on archive before it's even accepted, right? We want people to
yeah, I
know.
love that. By the way, I love that. That's how it should be.
Yeah,
So because yeah.
I think the basic research we have to keep it open, and in this age, say where there are always like say protection and we do basic science. Basic science should remain open, and so we publish. Yeah, we publish. We put on web. We give talks and we put on web. So yeah, we need to all have that voice. Keep the basic research open.
I completely agree. If Tesla hadn't put out the EV technology, I doubt we would have as much electric vehicles as we do now. It's about opening up the market. Wow, this is incredible. I don't come from a technological background so much so, or a scientific background, but thanks to this room, I've become infatuated with just theories, and not being from this background, I've been testing a lot of, well, out of the box theories, because I if I fail and fall flat on my face, I really don't care if I'm being judged, because, well, this is not my background. So I just thank you for just your action, thinking, rather than thinking and writing about it, you're actually doing. And that's what's so important. And Cecilia, I so much agree with you. Like changing the way we educate, the pedagogical aspects, and the utilization of AI for this, especially, is incredible. Like tailoring education to each student, and also, are there aspects of this that could be simulated through AI to actually accelerate your process and save you? time, because we've seen it in the pharmaceutical industry do, take years off of.
Yeah, that's a very good comment. I was talking to some of the people doing AI here at MIT. I say, hey, can you use your technology? Or wait, can we look at how big are the clusters? Because we have a spectrum measurement that we don't understand. It's very complex. It's in air. At this stage, we don't have a concrete progress there, but it's always good to talk to people, and you don't know what say some really a good idea could come up from people with no background. Like I said, my wife will work on say the content, and her comment that made us to do cloud experiment, right? So
So my question is she listed in the in the paper as a reference, like thank you to
yeah.
so and so? You should do an honorary reference in the future.
Yeah, I did mention her, thank her for suggesting the experiment. That's within the archive paper. Yeah.
Oh, okay, okay. I'll have to take a look. That's awesome, actually. Yeah, that's great.
Yeah.
I wanted to pick up on what Vincent was saying just a moment ago. I'm coming at this as a photographer, and generally I avoid green light, but you've opened my eyes, shall we say, and I can't wait to play with it. So thank you.
Thank you, Bob.
Bob, there is a question here, I think, on the room chat. Can you please check it so that we can ask Dr. Chen?
I do want to say one thing about the hand waving models. Our first model was quite literally a simple Newtonian model, and we ran it inside of a game engine just to see if hand waving and you squint your eyes and you stand a few feet away from the monitor, does it kind of look like the thing that you're wanting to see? So I don't want to dismiss hand waving. Hand waving can be very effective sometimes.
Thank you. Yeah, that's exactly because once we got a picture, let's say we go to experiment. I'm still working. I work myself on trying to develop this more rigorous theory. It will take time. It turns out even the photoelectric effect, Einstein got a Nobel Prize in 1900. See, his work was done in 1905. But the surface photoelectric effect, the theory was only developing in 1980s. So you can say it took a long time to actually solve some of those problems theoretically. Say the mathematical description.
Okay, so in the chat, VJ asks, has the light evaporation work been done with other liquids?
Excellent question. We tested some other liquids. This was 2021 and early 2022. And we saw effects. But later, we also found that at the time we had some problem with the light leaked into balance. So we started repeating our water experiment for another year. We had not gone back to other liquids yet. There's so many experiments that needs to be done, and I believe will happen, and probably depends on giving a picture, depends on the polarity, for example, dielectric constant. So yeah, I hope more people will say pursue this topic.
I have a question. Does atmospheric pressure or the change, is that a significant factor?
Uh, Humidity, yes. Humidity is a factor, and in fact, some of the experiment because we do in different time of the year, and they have different humidity in the lab. We don't have a too well controlled humidity environment, and then we have to say we have to wait until the right time. So yeah, we have to be careful on that. Yeah. that will basically affect the because when you have cluster coming to the air, it will break up, you will saturate. So that will depends on the initial humidity of the atmosphere.
Yeah, in our experiments, the advice that we got from Lee Cronin, Professor Lee Cronin, the chemist out of the UK, he said, listen, you got to do the experiments at 2 a.m., 2 p.m., at noon, at midnight. You got to do them at all hours just to get the randomness out of the way, because it could even be the technician that is just a skilled technician and nobody else can replicate it. So that kind of resonated with me when you were telling the story of the material fabrication, which ended up not even being a factor. So it's kind of an interesting process. In the end, we ended up going with you have to have a vessel or some sort of environment. We ended up going with a clean hood of the sort that allows you to kind of control for more of those parameters. But ideally, we'd want to do it in like a very much very controlled parameter. Just if not for the very reason that you want these tables of these values of these curves to be done really well, because then everyone else can use them to engineer stuff. I'm reminded of the Arctan story of von Neumann, who was saying, "Hey, look, I got the computer printing the values of von Neumann," but they're like, "But Mr. von Neumann, we have the values right here. They're on the table." He's like, "Yeah, yeah, but the computer computed them. You don't understand. We didn't measure them here. We computed them." And so I find myself sometimes being trapped in that kind of computer disease.
That's a good story. Yeah.
Yeah, Professor Chen, we've been here for about 1 hour and 34 minutes now. I just want to ask you, how much more time do you have for us?
I do have to go, and I wonder whether there are any other question. Maybe we can answer one more question.
Yeah.
I,
Just mine's real quick. Can we connect outside of this? I'll put my LinkedIn in the chat, and yeah, that'd be great. Thanks. If not, totally worth asking.
Send my email. Turns out I'm not really a social media person, and this is the first time I use a Clubhouse. But say send me an email. My email is gchen gchen number 2 at mit.edu.
Yes, sir.
Yes,
if I
so,
could take a quick question.
Rishi, okay, go ahead.
Yeah. So I think I'm I don't know how much I'm misunderstanding these concepts, but theoretically, water has a resonant frequency, and it's more likely to be energized at that frequency. So if I'm wondering if there are any applications for acoustically boosting your evaporation, say like use sound waves. I think we use acousto optics for 3D printing technologies to better guide like lasers into materials. But do you see any applications for increasing like the rate of evaporation by acoustically resonating the water at a particular frequency?
I certainly think that say disturbance of water surface by acoustic wave could lead to change the evaporation, and in fact, you flow more air across, you also have higher evaporation. For us, the at this stage, our focus is really understanding this basic light process, because that's a process that people don't know. That's a process is surprising, and we that's our focus now. But see, yeah, there are all this. See, once this process could be proven true, there are many other things one could do and combine other effects together.
Great, thank you.
Yeah, thank you so much, Rishi. So maybe there are more questions, but we can just invite Professor Chen at another time here, because he has to go, and I promised him only 1 hour and a half. So we respect his schedule. I'm trying to invite Darcel to come up the stage to help us do the countdown to close the room. And also, I would like to thank our co-moderators here, Rishi and Eric, who asked very important questions, and also Vincent, who came on stage, and everyone, to those who are listening, and to the others who came up on stage. So we are not doing rooms every day here. here now in quantum photonics because since last November I had been very busy in work and personally, so we may be going back to our regular schedules next year already. But we are having more rooms here, and I noticed because I had been screening the invitation for the speakers that we have, and we only have this is the eighth room wherein we are having conversations that we almost never want to end, and these are really benchmarking studies. And yeah, it gave me an opportunity to invite an eminent figure in our science history, Professor Gang Chen, to whom I would like to express our utmost gratitude for him being our guest speaker here. I hope, Professor Chen, that you had enjoyed your first Clubhouse experience.
Yeah, it's wonderful to have all this discussion and stimulating. And I want to thank you for your interest. Thank you for your invitation. And hopefully, I'll hear more from you, your thoughts, and feel free to share.
Yeah, thank you. Well, please come back soon. I will get in touch with you because I know you. It's this is not the only study that you're doing, so we are very honored that you came here. And yeah, at this point, I'd like to ask Bob if he has something to say before we turn over the mic to Darcel to help us close the room.
I think on behalf of everyone in the audience, this has been a spectacular night, and you've given us a bunch of stuff to think about. So thank you very much, Doctor.
Thank you.
So, Darcel, Professor Chen has to go now, although we don't want him to, but we have to let him go so that he will come back again because we keep our promise. So, Darcel, mic to you.
Thank you, Cecile, and thank you, Doctor, for a great room. To close the room, we're going to start our countdown from lucky number 7. Is everybody ready?
Ready?
Ready.
7.
7.
7.
Vincent 6.
Pick up sticks.
G5. No G.
G is our guest
5.
speaker.
Oh, wait. Sorry. No, you're not 5G. Sorry. Rajarshi 5. Sorry.
5.
IO4.
IO4.
Bob Tres.
3 it is.
Cecile Dos Equis.
Dos.
Good doctor, sorry for the stumble, but you are numero uno. Call out our last number, please.
1.
Thank you, Professor Chen. See you back here soon in Quantum Photonics. And to everyone, please check our platform for the next rooms. So we may have some newsroom in between, but I was losing my voice, so I hope I can have my voice better in the next few days. So thank you so much and good night.
Thank you. Happy holidays.
Happy holidays. Thank you so
Happy
much.
holidays.